Okay, so as you plan your week, so basically the only thing we have left to do is incline planes, which we'll do today. We got a lab on that tomorrow, review on Wednesday, so your test on forces is going to be on Thursday. Okay? Then your midterm final with 20% of your grade is probably going to be Wednesday or Thursday of next week.
So what do we do for the next weekend?
Projectile motion. It's like, it takes 3 days to get
projectile
through.
vomiting over all this.
Can we have the review like tomorrow so that we can start to work on it like
For the forces?
yeah, ahead of time?
I'll see what I can.
You're messing with his schedule, Kendra.
But like
What, you think
then we can
class
ask
president, you can
questions
do
like
whatever you want?
throughout the week versus
Wait,
just
does
the
that
day
mean we're not gonna have
before.
homework Friday?
No, you will.
No, it's Thursday.
I like it.
But it's not, it's just, it's a pretty simple lab. It's not all that.
Oh, it's a simple.
Okay. So,
If you
let's,
say rocket appliances one more time, I might turn my ears off.
okay, so let's talk about what happens in the lab. Okay? So here's the setup. All right, so let's look at what you did from the very beginning of this lab. You had a 10-gram mass suspended from the string. So let's look at this. What's the only force available to make this thing accelerate?
Gravity.
Gravity. Now, if you set the 10-gram mass up here on the cart, guess what's going to happen? Nothing. But if you take that 10-gram mass, that same 10-gram mass, and you suspend it from a string, oh, we get an acceleration. Okay? So, go back to the very first calculation. How did you get the net force on the very front page? With the 10-gram mass, what did you do?
You took the mass times
Which mass? The mass on the table, the total mass?
the mass on the string.
Okay? So we'll call this MH. Okay? So this is the mass that's hanging, the mass on the string. Whatever you want to call it. Okay? So, what did you do with that mass? Oh, I know, but to get the force, what did you do?
You multiply.
By what? By gravitational acceleration. On Earth, 9.8. Right? So, here's what you have to understand. This is the only force available to make the system accelerate. This is it. There's nothing else. There's no fans, there's no squirrels, there's nothing. Okay? This is it. This is the only game in town. Now, we're also assuming that this is a frictionless surface. So there's nothing up there impeding it. So here's the most common mistake that's made. You all say, well, this is an opposing force. It's not an opposing force, okay? It's not. The only way there's an opposing force up here is if there's friction, okay? Or you don't release the brake or something like that, okay? That's the only way there's an opposing force. Does this want to get accelerated? No. It's sitting there. It's happy. It's like I'm not, I'm just chilled out. And then all of a sudden this thing goes along and the string pulls and it goes, well, all right, I'm reluctant, but I'll go. So this begins to accelerate because of the force that's being transmitted through that string back to that point. Okay? That's the whole key, right? No, but you're going, but it doesn't want to get accelerated. You're right. How we take that into account is when we look at dividing the entire net force by the combined mass of the system. So this is taken into account when we divide by the total mass. Okay? That's when it's taken into account. Don't treat this as an opposing force. It's not. We take it into account when we divide by the total mass. So if you look at what you did, you said, okay, every equation starts with this, that force net equals force applied plus force opposing, and net force always equals mass times acceleration. Every problem start with this idea. Now, since it's frictionless, is there an opposing force? No. Okay? Don't have to worry about that. Drops out, goes to zero, easy peasy, nothing to worry about. So, your applied force is just gravity pulling down on that 10-gram mass. That's it. So that's my applied force, which then is also my net force. That equals mass times acceleration. Now, which mass are you going to use? The hanging mass, the mass on the table, or the total mass? The total
So you take the
mass.
total mass times the mass.
Oh, no. Not times. So it's the total mass, call it mass hanging plus mass on the table, times A. So you're going to take this net force and divide it by the total mass. Don't multiply.
So the applied force is just the.
Yeah, that's it. That's the only force available to make the system accelerate. There's nothing else. Okay, there is nothing else. Okay?
Okay.
Everybody cool with that? Okay. So, if you're not sure how to work, like when you get to problem number 10, you go, wow, I don't know how to do this problem. Go back to the first page and look at what you did and how you did that calculation. Literally, the only thing I did was change the numbers. That was it. That's all I did was change the numbers. So when you get to number 11, and I say, hey, come up with an equation to calculate the acceleration on a frictionless surface. Look at what you did. Okay, hey, I took the hanging mass, multiplied that by my gravitational acceleration, divided by that by the total mass, boom, there you go. That's it. That's all you have to do.
What? Yeah, I know.
We're good?
I mean, you said it pretty quickly. Yeah, the hang mass,
Times
the acceleration,
of gravity divided by the...
net force, or divided by the.
Okay, moving on.
I have my equation down. It's in
Okay.
my head.
That's all that matters. Now, so your acceleration on number 10 should be above a 4.0 GPA. Okay? Above a 4.0 GPA. Now, when you get to number 13, we're going to change the system because now there's going to be some friction, which is going to act as an imposing force. So your answer to number 13 for that acceleration, if you think about it, has to be less than your answer to number 10. Because number 10 is an absolute best case scenario. Okay? That's an absolute best case scenario if there's no friction acting in the opposite direction. Now we are going to have an opposing force. Now look, when you calculate the opposing force when there's friction, listen to me. The only mass you're going to use in mu equaling force friction over force normal is this mass. Whatever, you could have an elephant hanging by the end of this string. It's not going to affect the frictional force calculation here. Okay? So when you're calculating this force friction here, only use that mass. This has nothing to do with it. All this is doing is making the system go. This mass has nothing to do with that force friction up there. Okay? Nothing to do with it. Nothing. Not a zip. Oh, bad. Okay? So your acceleration on that one when there's friction should be a little bit less than 4. Okay? A little bit less than 4. Not a whole lot. Just a little. Okay? Just a little bit. Wee bit less than 4. Okay? Just a little bit?
No, like seriously,
I
I
have
don't know
no
what I was doing.
Okay. Now, here's what I want to look at. And here's this transition that we're going to get into today. So, here's what I want you to look at. Is that, and there's a reason I specifically chose the 200 and the 240 grams. Okay? So, if it's an outward machine where this thing, they're just hanging on either side of the poles. Here's your 0.24 kilograms. Here's your 0.2 kilograms. Right? So, this is my applied force going this way. This is creating an opposing force because of gravity. The difference between those two is your net force. You still divide by the total mass. Okay? So what you should see when you get to number 17, right? That should be a relatively small acceleration, much smaller than what you calculated up above. And here's the reason why. With this one, this other mass is acting as an opposing force because gravity is actually acting against it. But look what's common. No matter where I put the masses, I still end up with the same total mass. At the end of the day, I still divide the net force by the acceleration. But because I ended up with a much smaller net force, I end up with a much smaller acceleration. Now, you guys did this with our flat surface, and you said, okay, right, here's this mass being suspended, this is being drug along, this does not act as an opposing force here. So then, here's the transition. I said, okay, let's put this thing at a wee bit of an angle, okay? So we got something like this happening. So this is like an in-between. This one, when it's flat, there is no opposing force. This one maximizes the opposing force because of the fact that it's completely hanging up in the air. This one is somewhere in between. So I've got a little bit of an opposing force here, okay? Not a whole lot, but a little bit. So this acceleration should have been less than when it was flat. And this is what we're going to get into today on these inclined planes. So whenever you have an inclined plane, there's a component of this gravitational pull that acts down the inclined plane that works against an applied force going up. Okay, so this is like a transition. This one, there is no opposing force. This maximizes the opposing force. If you're on an inclined plane, you're somewhere in between. Okay? Makes sense. We're good. Now, all of your statements on number 9 should be false. None of those are true. Okay? And when you get down to C, don't tell me C is false because it should be negative. No, this has nothing to do with it. Okay? So if you don't say, oh, C is false because G is negative, no, bad. It isn't why it's false. Okay? Yes, Kendra?
How do you tell if you're using the negative 9.8 acceleration versus like the positive 9.8?
Well, like on this deal, since all you're doing is you're just finding the two forces and you're subtracting them anyway, you're just using 9.8 and then you're just looking at the difference between the two of them.
Yeah.
Okay? If the only time you really have to make it negative is if like if you just have a rocket, right, that's taking off, and your applied force is some positive value, like 20 newtons, then your opposing force has to be a negative value.
What if you're on that inclined plane then? How do you...
And this is what we're going to get into today, it really doesn't make any difference. If you want to make your applied force positive, then your opposing force would be negative. If you make this negative, your opposing force would be positive.
So like on 12 on this one, it doesn't matter if it's negative or positive, for example?
No,
It doesn't?
I just always make my applied force positive,
Okay.
and then I'm making the opposing forces negative.
Okay.
As long as they have opposite signs, it really doesn't matter.
As long as, yeah.
Okay, it
That makes
literally
sense.
doesn't matter.
Okay.
Okay?
How do you do 14 and 15?
Use that.
That is that.
Yeah. The applied force is the bigger one, the opposing force is the smaller. And the difference between them is your net
I
force.
got done 4.
Okay, anything else? Going once, going twice, sold. Okay, okay. All right, so you've got the notes on inclined planes. So this is like the last big topic. So all we're to do is basically build on everything that we've talked about so far. So there really isn't going to be like a new concept. We're going to throw in a little bit of trig, but it's going to be the exact same idea. So here I've got a perfectly flat surface, no acceleration is happening.
I hate you.
Why is there no acceleration? There's one of two options to to explain why there's no acceleration. Either A, there are absolutely no forces acting on the system and it just remains at rest, okay, because inclinatio ad quiddum, or there are forces acting on the system but everything's just balanced out.
Second.
Second, okay, gravity's pulling down, the table's providing an upward force.
Wait, is that ever possible to have no force acting on the number?
If you're in deep space, you could conceivably get a situation where your gravitational poles even then are effectively zero. But you've got to go in deep space. Okay. But technically you're never in zero gravity anyway. Okay. So here's the deal. But if I give this any kind of a tilted all and let go of it, it begins to accelerate. So let's start with the basics. When I let go of this, every time, which direction is this thing going to accelerate? Downhill, right? Okay. For those of you that have been snow skiing, I promise you there are a lot of things you have to worry about. When you get off the ski lift at the top of the mountain, you never have to worry about gravity pushing you farther up the hill. Okay? It's not, if that does, even in Colorado, that's weird. Okay? So, just saying. So, even when you get off there, no matter what, you know gravity is going to pull you down that hill. So, rule number one, gravitational pull is always going to make you go down the hill. Now, so let's look at this. So if I have just a little bit of an angle, I get just a little bit of an acceleration. If I lift it up higher, what happens? Get a bigger acceleration. So what's the only way that I could create a bigger acceleration?
By
Increase the angle.
Yeah, but by increasing the angle, I make the force bigger or smaller? Bigger. Okay? So the steeper I go, the bigger the acceleration is. So if I take this to an extreme, right, and make it completely vertical, as soon as I let go of it, I get an acceleration of 9.8. So here's the deal. If it's a flat surface, I have no acceleration. If I'm at a vertical situation, I have an acceleration of 9.8 meters per second squared. So if I'm at any point in between 0 and 90, I'm going to have an acceleration somewhere between 0 and 9.8 meters per second squared. Okay? Everybody cool with that? Okay. So when you look at inclined planes, there's always three forces that you have to worry about. There are always three forces you have to worry about, no matter what. So let's say that we've got a block with a mass of 1.02 kilograms. Now, no matter what, you always start with the gravitational force created by the Earth. So if I got a mass of 1.02 kilograms, what can I always find if I know the mass? I can find my FG. Trust me, if I take 1.02 times 9.8 meters per second squared, I get 10 newtons. Now, that always acts straight down. Okay? No matter what that inclined plane is, no matter what the angle is, doesn't make any difference. That always acts straight down, technically towards the center of the Earth. Okay? So this thing is being pulled towards the center of the Earth. No matter how I change that angle, this number is not going to change. It always acts straight down. Boom. No exceptions whatsoever. Now, here's, if you go back to what Kindred asked earlier. Do I have to make this negative? Do I make it positive? I don't know what to do. All you're using the 10 newtons to do is to get a bunch of other numbers. So this is just like a gateway force. Okay? Don't worry about making it negative. Just get the number. We'll define the whole system later. Okay? So when you get this value, just get the number. We're going to use that to get a whole bunch of other numbers later on. So just get a number, take the mass times gravitational acceleration, just like you've done 100 times. Don't worry about making it negative, just get a number. Now, there's going to be two other forces. One of the forces that we just showed acts to make this thing go down the hill. And that's what we're going to call force parallel. So there's a couple of different ways you can draw force parallel. I'm going to draw both of them so it's a personal preference thing. So some people like to draw your force parallel coming out like this, okay? Because oddly enough, it's parallel with the inclined plane and it's a force, hence the term force parallel. Catchy title, I know. So some people like to draw it here because that's the direction it's going to act. For those of you that are geometric purists, there's another option. So if you go through the geometry, this is going to be some angle, 30 degrees, 20 degrees, however you set the inclined plane. Now, here's where this can be shifted. I can take this parallel force here, and I can move it down here, so that, wait for it, it's still parallel with this. Okay? So no matter where you draw it, it's still going to be a parallel force. Now, this is where the normal force comes into play. The normal force is created by the surface. I still have to have this track providing an upward force to keep gravity from pulling it down. So your normal force always acts at right angles to whatever surface that you're on. So my normal force is acting like this. So this is my Fn. So here's where a whole bunch of things kind of come full circle. Whatever angle this is whatever angle this is. Okay, if you go through the geometric proofs, alternate angles and all this good stuff. So if this is a 30-degree angle, this is a 30-degree angle. If this is 50 degrees, this is 50 degrees. It's the exact same angle. Doesn't make any difference. Now, so here's the deal. This Fg is your gravitational pull. That's the number that you will always know. You will always know that number. No exceptions. You'll always know that number. So, if I know this number, which is the hypotenuse, Miss Treadway, how can I find this force parallel over here?
If you know both of the other sides, is that what you said?
Yeah, I know this. This is my hypotenuse. And I know this angle. I'm trying to find this, which is the side opposite of that angle.
No, hold on. I've forgotten. I don't know.
Mr. Gilchrist, help out your partner.
Sine.
Sine. Because the sine is the opposite over the hypotenuse. Right? So, to get my force parallel, I can look at this and go, okay, sine of the theta is going to equal that force parallel over Fg. Boom, there we go. So, I know my Fg, I know my angles, the only thing I don't know is force parallel. So force parallel is always going to be Fg sine theta. That's why on your equation sheet, you've got this. This says force parallel equals Fg sine theta. This is where it comes from. Okay? Now, Miss Treadway, if I use sine to get my parallel, my normal, I'm going to use beautiful. So my normal is going to be force parallel, or Fg times the cosine of theta. Now, back on the very first day when we started looking at forces, and I said, this is how you technically calculate force normal, is that it's Fg cosine theta. Okay, this is how you do it. Well, look, in reality, this is where this comes from. But if you're on a flat surface, you're taking the cosine of 0. The cosine of 0 is 1. And that's why on a flat surface, force normal was the same as Fg. So on inclined planes, listen to me, listen to me, listen to me. On inclined planes, as long as this is a non-zero angle, you cannot say your normal force is the same as your gravitational pull. It won't work. Now you have to be cognizant of this angle. Okay, and this is where it comes from. So there's a new game in town, and you can't say, oh, normal is the same as Fg. You can't. You have to use the cosine of that angle, and calculate that normal force. Okay? Now you have to take it into account. So this is where you can draw this differently. So here are your two options. If you're a triangle person, which this makes this a right angle, and you like triangles, oh, I like triangles. Good, happy for you. Okay? So you can come down here and you can draw your force parallel here, and your normal force coming up like this. This makes this a right angle. That's a right angle. You know your angles. Boom, hey, groovy, cool. Enough with the head nod. Seriously, I'm starting to get dizzy. Quit. That's like teaching a bunch of chickens. Okay. Now, here's the other way that you can draw this, and I don't care how you do this. The other option is that you draw the block, you draw the FG like this, you put your force parallel like this, and then you draw your force normal coming up like this. But if you're going to do this, this normal force doesn't point straight up. It acts at a right angle to the surface. Okay, so if you're going to draw it this way, you have to make sure that this is a right angle to this surface. I don't care which one you do. Okay, either draw it as a triangle, draw it like this. If you're a purist going, well, this is actually where the forces are acting. I don't care. Doesn't make any difference. This is how it has to be set up. Okay? All right, Patty, stop that. Let's go back.
Excuse me, sorry.
Okay. All good. All right, ready? Okay, so what I've got set up here is kind of a different way that you can show all these forces. So I've got a cart sitting on an inclined plane. So if I cut this string, what's going to happen?
Gravity.
Like gravity
And its
isn't happening
finest
now?
aspect.
I mean, it depends. What is that? Is it this?
What do you mean?
At the top.
You got a lot of strings.
Yeah,
I do have a lot of strings. If I cut this string,
Gravity is going to be applied.
gravity isn't applied now.
Gravity is going to
Gravity is waiting.
overcome the opposing force.
What's the opposing force?
Whatever
Those
you got.
plates right there.
Okay. So basically, because even if I like take the tension off this, it doesn't go anywhere. So, but if I take the tension off of here, it does begin to move. So what this is doing is balancing out the force parallel that's acting down the inclined plane. Now, if I take this board and I slide it out, okay, system remains in equilibrium, right? So, because look, notice that this string right here is at right angles to the surface of that cart. So what this is doing, this is providing the normal force. This is what allowed me to pull that board out. So if I put that board back in there, okay, and I take the tension off, then I still need the board. So the board or this string has to provide the component of this gravitational pull that's acting to keep this thing from falling down. So imagine that you have three forces. Gravity is acting straight down. You have the normal force that's acting at right angles to it, and then you have this force parallel which is acting down. So when I pull this thing out and it doesn't accelerate, that means all of the forces add up to zero. So I got the gravity going this way, I got the normal going this way, I got this going this. So if you connect all of the arrows in a tip-to-tail method, where do you end up?
At the origin.
At the origin, and the system doesn't accelerate. Okay? So, but right now, like if I try and take this tension off, it's going to fall. If I try and take the tension off here, it's going to fall. So I can, if I put this board back, here's what you have to realize. I can take the tension off here because now this board is taking up that weight. So visualize this. Here's the leap of faith with the normal force. Imagine that I had a very, very small Newton scale underneath here. So right now, imagine that there's just basically there's just a very, 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 very tiny amount of space between the board and the cart. The scale would be reading 0 right now. if I take this off, and then the reading on the scale would go up. So the reading on the scale is going to be whatever the weight of all this is. So in this case, I've got 445 grams. So if I take 445 grams, 0.445 kilograms, multiply that by 9.8, that gives me the value of my normal force. Out here, I've got 130 grams. I've got 130 grams suspended from here. If I take 0.13 kilograms, multiply that by 9.8, that's the value of my force parallel that this thing is overcoming. So you always have these three forces, no matter what. If there's friction, inclined planes, snow, doesn't make any difference. You always start with these three. Gravity acting down, parallel acting down, normal acting up. You always have those three. Got it? Good. Grant, back to you. And let's work off of a 30-degree angle. Go with a mass of 1.02 kilograms. So here's situation number one. Situation number one.
Don't give me that.
Are we good? Okay. Okay. Situation number two. Situation number one. I've got a 1.02 kilogram mass resting on a completely frictionless surface. And I'm just going to let go of it. And what I want to know is what's the acceleration of the system. Okay? There's no friction, there's no squirrels, there's nothing. I'm just going to take this mass, I'm going to put it at a 30-degree angle, and I'm just going to let go of it, and I want to know the acceleration. So here's the deal. It goes back to the standard idea. As soon as you say, hey, what's the acceleration, what do you know your net force is not going to equal? Zero. That's what I do know. I know it's not going to be equal to zero. So you go to this. Start with this. Force applied plus force opposing. Okay? Now, I'm going to add something to this. Okay? I'm going to add something to this situation. Because I'm on an inclined plane, there's also going to be a force parallel. Okay? Which is different than the applied, which is different than the opposing. So now I've got to introduce a third variable in here that I don't have to worry about on a flat surface. Now, technically, you could always introduce force parallel into a flat surface, but on a flat surface, what's your force parallel always going to be? Zero, so you don't have to worry about it. So technically, this is always here, but we don't worry about it. So here's the deal. I've got this block here, and I'm just going to let go of it. So what's my applied force? Don't make this difficult. What's your applied force? Zero. I'm just going to let go of this thing. I don't have, there's no gears, there's no rocket engines, there's no sails, nothing. That's just going to be a zero. Is there any opposing forces? It's frictionless. Those are zero. So what's the only thing that I have to make this thing accelerate? Force parallel. That's it. So my net force is my parallel force. Okay? Simple. So, but I don't know what my force parallel is. But I know this is a 1.02 kilogram mass. So I know this is going to be 10 newtons. So how can I get my force parallel? What am I going to do? Yeah. So I'm going to take 10 newtons. So my force parallel is going to be my 10 newtons times the sine of 30 degrees. Sine of 30 is 0.5. I get 5 newtons. Okay? So now I've got my force parallel. Now, this is what you have to decide. Here's the big decision that you have to make. And I don't care how you do this, but you need to make a decision. This becomes like a new x and y coordinate system. Okay? So you need to decide, do you want downhill to be negative or do you want uphill to be negative? I don't care. Okay? It makes me no difference. Literally, makes me no difference. Liz, do you want down to be negative or down to be positive?
Positive.
Okay, fine. So in the Liz coordinate system, downhill is going to be positive. Fantastic. There is no right or wrong answer. If you go, I like downhill to be negative, fine, make downhill negative. I don't care. But once you establish a system, you can't change it within that problem. When you get to the next problem, you can change it. If this doesn't work out for you, you go, oh man, I didn't choose wisely. Should have made negative. Okay, fine. When you get to the next problem, change it. Okay? So this isn't like a decision that you make for the rest of your life. Like on this problem, and once you choose this, you can't change it later on. No. Every problem's a new beginning. Sounds kind of 60-ish. Okay. So, I got a 5 Newton force. Now, at the end of the day, here's what I've got. I got a 5 Newton force acting on a 1.02 kilogram mass. How can I get the acceleration?
Force divided by mass.
Force divided by mass. Once you figure out what the force is, then just use F equals ma. So at this point, I'm going to take 5 newtons, I'm going to divide that by the mass of 1.02 kilograms, and I'm going to get 4.9 meters per second squared. There you go. Now, here's where this gets a little bit odd, but it's just because of the way the trig functions work. Most people, if I said, at what angle would you get an acceleration half of 9.8 meters per second squared? Most people would say at about a 45-degree angle, because that's like, okay, well, if this is 0 and 90 is straight 9.8 meters per second squared, 45 degrees should be the 4.9, okay? It doesn't because of the way the trig functions work. So 30 degrees is actually when you get your 4.9 acceleration. It isn't at 45 degrees. So I just want to block that out right now. So here's an option. This is an option. It's cool. It works. Fantastic. Grand. But here's another thing that you can do if you're into just pure numbers. Here's the other thing that you could do. You could say, all right, force net equals my force applied plus my opposing force plus my force parallel. Okay, that's cool. Those go away. Okay, force net is ma. Now, how do you calculate force parallel? Generic way to calculate any force parallel. What do you need? You need two things. The sine of the angle and, no, mass. Right, the FG, which is going to be mg sine theta. Right, mg gets you your value of your gravitational pull. Well, I have ma equals mg sine theta. What happens to your mass? So you get A equals G sine theta. Now, if you remember back to the lab that you did where you pushed the cart up the ramp, okay, and I said we're going to use this to get a theoretical acceleration for the ramp, assuming that it's frictionless, this is where that equation came from. You're assuming that the only force acting on it is gravity. You take 9.8 times the sine of the angle. And this always works. So look at it this way. If you're on a flat surface, what's the sine of 0 degrees? 0. So your acceleration is 0. Now, if you go to 90 degrees, what's the sine of 90? 1. 1 times 9.8 gets me 9.8. So my acceleration, if I'm just straight up and down, gives me 9.8 meters per second squared. Okay? So, be careful of this. It's a nice thing. But be very, 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 very careful, because this only works if it's a frictionless surface. If there's any friction at all, you can't do this. So this is why I don't have this on your big dog equation sheet, because you go, oh, acceleration is always g sine theta. It is if I tell you that there's no friction, but most of the time there's always friction. Okay? So it's a good theoretical calculation, but in reality we really can't use it that often. Okay. Now, so, that's chemistry.
Way to add friction to that equation.
Now, I want to go back to this problem. It's still frictionless. Mass is still 1.02 kilograms. I still got my FG. We'll stay with the Liz system. My force parallel is positive 4.9 newtons. Now, what I want to know is how much force do I have to apply to pull the block up the inclined plane at a constant velocity. So I want to pull this thing up at a constant velocity. How much force do I have to apply? Now, what are the two most important words in that question? Constant velocity. Therefore, the sum is 0. So my net force is going to be, so my acceleration is, so that means all of the forces have to add up to 0. Now, you go back to this. On an inclined plane, you always have three forces. You have force parallel, you have force opposing, and you have force applied. I'm still frictionless. So is there any opposing force? No. So that's still 0. So what's the only way these two values can add up to 0? If they are opposite. So if you go with Lewis' system, if you're defined this direction as being 4.9, which direction is your applied force going to act? Up or down? It's going to act up, right? Because that's the direction that I want to push it. So here's the deal. So if you're going to stick with Lewis' system, and you're going to make down being 4.9, and that's positive, then my applied force has to be negative 4.9.
Sorry, Burkamp.
Gravity storm?
Yeah.
So that's going to be negative 4.9 newtons. Like I said, I don't care how you do this. I literally do not care. If you want to make down be negative, fine. Then your applied force is going to be a positive 4.9 newtons. Doesn't make me any difference. Okay? But again, once you establish a system in a problem, you can't change it. So in other words, if you're going to make this be positive, your applied force can't be positive as well. Your applied force has to be negative. Good with that? Good? Got it? Now we're going to change the system. We're still going to keep the 30-degree angle. We're still going to have a mass of 1.02 kilograms. But now I'm going to tell you that mu is 0.1. So now what do we have? Friction. So here's the setup. Okay, here's the setup. I'm going to let go of this block. And I want to know what's the acceleration of the system. So I'm going to set it here. Okay, 30-degree angle. I'm going to let go of it. I want to know what's the acceleration. So what do I have to find? There's any number of things that I have to find. I know what my FG is. That's still 10 newtons. Okay. My force parallel is still 4.9 newtons. Now, do you want to stick with down being positive, or do you want to change it up?
Change it up. Change it up.
You want to make it negative?
Yes.
Okay. All right, we'll make it negative. Fine. It's a new problem, new day. We can make it negative. Now, here's the question. Brooklyn, which direction is friction going to act? Up the hill or down the hill? Up? You sure? You're right, you should be. Okay? Because which direction does friction always act? The opposite direction of motion. Okay? So before we do any calculations, let's think this through. Let's just think this through for just a second. My acceleration, no, that force parallel was 5 newtons, not 4.9. 5 newtons. My bad. That was 5 newtons. So my acceleration was 4.9. So if my acceleration is 4.9 meters per second squared without friction, now that there is friction, what should happen to my acceleration? It should become less. So right away, I know that I should end up with an acceleration less than 4.9 meters per second squared. If I don't, I've done something wrong. So, mu equals what? besides 0.1, how do you calculate mu? It's the ratio of
Force friction.
force friction over
Force normal.
force normal. Now, here's what you can't do. You can't sit here and go, oh, my normal force is also 10 newtons. You can't do that because you're not on a flat surface. You have to calculate that normal force by using Fg cosine theta. So, this is going to become U times Fg cosine theta is going to equal my force friction. So all I did was multiply force normal over here, and then force normal was Fg cosine theta. So all I did was a simple substitution. This isn't anything radical. Oh, we've never seen that before.
Is that mass or?
Huh?
Is that mass or?
This?
Yeah.
No, that's just mu, coefficient of friction.
That looks like an.
That looks like a mu. Those are my m's.
I'm just making sure, you know.
Okay, I
multiply
understand.
mass.
I
Like, what do you
understand.
do in Garfield? And then I'm like,
Then you get mass squared and it's just going to be weird. Okay, so somebody take, let's just get my normal force. Take 10 newtons times the cosine of 30. It's 8 point something. 8.86 or 8.66, one of the two. 8.66. Okay, so I've got 0.1 times my normal force, which is 8.66 newtons, and that's going to give me my force friction. So this is going to be 0.866. Now, so here's the deal. This is where you have to stick with your guns. If you're going to make that force parallel be negative, okay, then this force friction has to be, because now it's acting up the inclined plane. So that's why I said, I don't care how you set up the system. I don't care. But once you start with it, you have to stay with it. So if this is going to be negative 5 newtons, then my force friction is going to be 0.866 newtons. Now, look at this. Beyond all the formulas and all that good stuff, look at the big picture. Gravity's pulling this thing down with a force of 5 newtons. Friction's acting up at 0.866. What's going to be the net force? The difference between the two, right? So this is pulling it down, friction's making it go up. So this idea that my net force is the difference between my force parallel and my frictional force. If you're a downhill skier, you live by this relationship. Because on the ski slope, everybody's going to end up with the same theoretical acceleration if it's a frictionless surface. So if you look at skiing, like in the Olympics, downhill skiing is nothing but an application of force parallel. That's all it is. Everybody has the same theoretical acceleration because everybody's on the same inclined plane. If you win, you minimize your frictional force. With a smaller frictional force, you end up with a bigger acceleration, you go faster, you take less time going down the hill. So this is why they wear very aerodynamic suits, they have the aerodynamic helmets, and this is why they're in a tucked position going down the hill. Because they're not going to go down the hill like this, wow, look at me. Okay? It would be cool, and every physicist in the world going, you're a schmuck. Don't you understand? You're increasing your surface area and your force friction. You're not going to win. So basically, if you're going to win in downhill skiing, you minimize your frictional force. Therefore, you get a bigger acceleration. There you go. Okay. All right. So now we can look at mathematics. So now we can sit here and go, okay, force net is going to equal my force parallel plus my fat plus my phi. Now, all I did was let go of the box. So there still is no fat. Okay? All I did was let go of it. There's no applied force. That still is 0. I don't have to worry about that. We said my force parallel was negative 5 newtons. Now, my opposing force is going to be going up the hill, and that's going to be 866. So somebody say, so that should be
Negative 4.144,
0.144 newtons.
something like
Okay.
that.
3?
Yeah, 4.13.
Okay? Now, what's happened to my net force now that there's friction? Net force has become smaller because now I have friction that I have to overcome. Groovy. Now, how am I going to get my acceleration? So somebody take that and divide it by 1.02 kilograms. Negative what? 4 point what? Now, what's happened to my acceleration now that there's friction? It's gotten smaller because now I have friction that's acting in the opposite direction. Okay? Good with that. So, if friction becomes, let's say that coefficient of friction goes to 0.2, what's going to happen to my net force? It's going to go, no, if my coefficient of friction goes up to 0.2, if mu goes to 0.2, what's going to happen to my opposing force? It's going to go up, so my net force will go, and my acceleration will go down. Okay. Now, so here's the last of the problems to work with. Okay, now we're going to tie everything together. So, if you do this one, you're in good shape. Let's start over again. Same 30-degree angle. Same box. 1.02 kilograms. Fg is still acting down. That's still 10 newtons. Now, you want to stick with force parallel being negative, or do you want to change it back to positive?
Keep it negative, please.
Positive.
Hammett spoke first.
All hail Hambone.
Okay? Now, here's what I want to know. I want to know how much force does it take to pull it up at a constant velocity.
Man, that's pretty hard.
Okay? So here's the block sitting here. Here's my Fg, here's my force parallel. Mu is still 0.100. So now, visualize this. I want to pull this block up this inclined plane at a constant velocity. How much force is it going to take? What was that? 4.13 newtons. Guaranteed.
What is it?
Okay? Everybody cool with 4.13 newtons?
No.
You should not be.
I'm not cool with that, Grant.
Okay, here's the deal. Which way is this block going to move? Up. Which direction is friction going to act? Down. Because your frictional force, remember, always acts in the opposite direction of motion. Okay? So now, instead of my frictional force acting up, when I let go of it and let it slide down, now I'm pulling it up, so now friction is acting in the downward direction. So now, my force friction is going this way.
What?
Okay? Now, is it still the same frictional force? Yeah. But now, if you're defining down as being negative, now what's the sign of your frictional force? It's also negative because the block is going this way, but friction's acting.
Oh, that's pretty. We're just pulling it up.
Yes!
Simple.
Maybe 5.
So my force friction is negative 0.866. So my total force then is going to be 5.866 newtons. Everything adds up to equal to 0. I don't have a net force. Life is good. Okay? So that's why I said be very careful about going, oh, friction is always negative. It depends upon how you set up the system. Friction might be negative. Friction might be positive. But that's why it is so vital at the beginning that you establish a system and then you stick with that system. Okay? All right, so shut that down. Or just eat the peel with it. It's probably tasty.
Why did you?
Okay, all
I
right.
love
So
this.
let me get through this right quick. So this is why I said it doesn't make, when you calculate that gravitational force, all you're using that number to do is get a bunch of other stuff. So when you get the gravitational force, just get a number. Don't worry about making it negative. If you're really dead set, oh, I always like to make FG negative. Fine, make it negative. I don't care. Okay.
Wow, only one side.
Yeah, only one side.
That's weak.
Oh, there's a lot to it. There's a reason I didn't have give a
Because we
back
gotta
side.
sketch all forces.
Yes, exactly.
Ah.
So, anyway,
Every vector. Like, oh my gosh.
so on 1 and 2, all you're doing is you're finding the numbers, okay? One's a 20-degree angle, one's a 60-degree angle. That's it. Then, as the angle increases, what happens? Gravitational force, normal, and parallel. When you get to problem number 4, 4 is going to get you all the way through number 8. So once on number 4, here's the setup. I got a 1.2 kilogram box on a 20-degree hill. And your system uphill is defined as blank, downhill is defined as blank. There are no right or wrong answers on number 4. I don't care how you do it. But once you set up number 4, that's going to remain the same system all the way through number 8. Okay? So choose wisely on how you set up number 4. Because once you set the parameters on number 4, there's no turning back. So, on these that have the asterisk, on the back side of this or on another sheet of paper, I don't care. I want a sketch. I did not say that you have to draw this to scale. But I want a sketch where all the forces are labeled. Okay? And don't draw these tiny little vectors and expect me to guess what they are. Okay? So you can either do it on another sheet of paper, you can do it on the back of this. I don't care. So on any of those that have an asterisk, and there are 4 of them, I want a sketch. Okay? I want a sketch. So you can do it on the back, another sheet of paper, I don't care. Now, when you get to number 9 and 10, the 2 most important words on there, because I was nice and bolded them and even underlined them, you're at a constant velocity. So on 9, you're going to pull this thing up a frictionless inclined plane at a constant velocity. Number 10, there is friction. You're still pulling it up at a constant velocity. So make sure on all of those, no matter what, you will always have a minimum of 3 forces. Parallel, normal, and gravity. So no matter what on those forces, you always have those 3. You might have an applied force, you might have forced friction, but you will always have those 3. Okay? All right. So we're done.